Hello, I am Professor Sukruti Joshi from Department of Applied Science Chemistry at Royal University Ahmedabad. Today we are going to learn about acid and base concepts. Before we are starting about the concepts of acid and base, we have to know that what are acids and what are bases. So firstly, acids are the substances which generally you can say which corrode anything, and bases are the substances which have the nature alkali. So basic properties of acids and bases are given here. That is acids. The first we are taking the properties of acids, and second is we are taking the properties of bases. So acids, basically acids which turn blue litmus paper into red. They taste sour. Acids corrode metals. They are basically a positively charged hydrogen ions, can be represented by H plus ions. Next is the properties of bases. They turn litmus paper, blue litmus into red litmus into blue. They taste bitter. They are basically a negatively charged hydroxide ion represented by OH minus. They feel slippery and basically they have alkali nature. Now most hand soaps and drain cleaners are bases, and strong bases are caustics. You can say caustic sodas have their basic pH. So you can say that acids are the substances which have the pH from 0 to 6, or you can say below 7, and bases are the substances which are above 7, that is 7 to 14. As you are come near to your neutral value, at that time you are getting the weak point, while strongest will be on the nearby to 1, 2, 3, something like that. And the same way near to your 12, 13, it is strong, 12, 13, 14, and at 8, 9 you are getting weak bases. So we are going to learn here three basic concepts of acid and base. First is Arrhenius concept, second is Lorentz-Bronsted concept, and third is Lewis concept. Here, these three concepts are given by different scientists as they have to explain all these things, and they are just explaining what are acids and what are bases in their own languages. Depending upon that, these concepts I come across that what are acids and what are bases. Three different concepts in this. Now first concept is Arrhenius concept of acid and base. According to Arrhenius concept of acid and base, an acid is a substance that when dissolved in the water, it increases the concentration of hydrogen ion, hydronium ion, or you can say hydronium ion, that is represented by H3O+. As we know that here, chemists often use the notation of H+, notation H+, for the H3O+ ion and call it the hydrogen ion. Now we know that hydrogen ion cannot be present in the water in free form, and it is always binded to the H2O. Therefore the whole form is known as H3O+. Hydronium ion is also known as hydrogen ion. So here remember, however, that the aqueous hydrogen ion is actually chemically bonded to water, that is H3O+. So both are the same things, H3O+ and H+. So here just write that when you are dissolving any substance into the water, at that time it increases concentration of H3O+, or you can say H+. That substance is known as acids according to Arrhenius concept. Now, according to Arrhenius concept of acid and bases, an acid is a substance which increases concentration of H+ ion. Same way, Arrhenius concept of base, according to that concept, a base is a compound which when dissolved in the water, it increases concentration of hydrogen, it increases concentration of OH minus ion, that is your hydroxide ion. That thing is known as base. Now, in the Arrhenius concept, a strong acid is a substance that ionizes completely in the aqueous solution to give H3O+ and an ion. Here the definitions of what is a strong acid, what is a strong base, what is weak acid, what is weak base, what is conjugated acid, and what is non-conjugate acid. Whatever is given here, like this ways only. Here an example of perchloric acid is given, that is your HClO4. When HClO4 dissolved in the water, it ionizes to H3O plus ClO4 minus. Here we can see that H3O plus, the concentration of H plus will be increased as the perchloric acid will be dissolved in the water. As of this way is going on, H3O plus is dissolved, H2O plus concentration will be increased and ClO4 minus in the reverse reaction it goes back and again form HClO4 and H2O. Again same reaction will come across. Now the strong acids which include the strong acids are HCl, HBr, HI, HNO3 and H2SO4. HCl is your hydrochloric acid, HBr is your hydrobromide acid, HI is your hydrogen iodide and HNO3 is your nitric acid and H2SO4 sulfuric acid. Hydrogen iodide, hydrogen bromide, HCl hydrochloric acid, HNO3 your nitric acid and H2SO4. Here if you can give this number, HNO3 is the strongest, after that H2SO4 will come, after that HCl and HBr and HI. Likewise the whole sequence from strongest to weakest continuous. Now in the Arrhenius concept, a strong base, here the definition of strong base is given. In Arrhenius concept, a strong base is a substance that ionizes completely in an aqueous solution to give OH minus and a cation. Here it gives OH minus ion, while there it gives your H plus ion. The example of sodium hydroxide, that is NaOH, is given here. NaOH when dissolved in the water, it gives you Na plus and OH minus. Here it increases concentration of OH minus ion. Therefore, it is known as strongest base. It ionizes itself completely to form OH minus, or you can say hydroxide ion, and therefore it is known as strongest base. Other strongest bases are LiOH, KOH, CaOH twice, SROH twice, and BOH twice. This is your lithium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide and BOH twice, that is your barium hydroxide. These all are also strongest bases which you can consider with NaOH. Now the next definition which is given is weak. The definitions of weak. So most other acids and bases that you encounter are weak. So along with all these things, like as you know that what are the strongest acids, what are the strongest bases, so other things or other acids and bases, they are almost weak. They are not completely ionized and exist in reversible reaction with the corresponding ions. Here they doesn't ionized each and every way, like they are not completely ionized and they remains as it is. It can give in the reversible reaction, it can participate in this reaction. One example is given of weak acid, that is your acetic acid, represented by HC2H3O2. When HC2H3O2 is dissolved in water, at that time it gives you H3O plus C2H3O2 minus. Here H3O plus, it produces H3O plus but not ionized completely, and it participates in the reversible reaction and again goes back and form acetic acid and water. Therefore this is known as weak acid. Second example is of weak base, ammonium hydroxide, that is NH4OH. It is a weak base. Why? Let's see here. NH4OH when dissolved in water or when ionized, it forms NH4 plus OH minus. Here also you can see that it forms OH minus ion, and so it is known as base. But what it participates in the reversible reaction. This is NH4 plus and this OH minus both get together to form NH4OH. Therefore this is known as weak base. NH4OH is weak base, while acetic acid is weak acid. Now, limitations of Arrhenius concept. What is the need to go for any other concepts? Like why we are going for Laurie-Bronsted concept and for Lewis concept? Because of the limitations of Arrhenius concept. Limitations of Arrhenius concepts are given here. The first and the most important is the Arrhenius concept is limited in that it looks at acids and bases in aqueous solutions only. So here it only considers that if we dissolve any substance in the water only, then if you get the higher concentration of H plus, then it becomes acid, and if we get higher concentration of OH minus, then we get base. But when we dissolve any of the substance in any other solvent, then what happens? It cannot be explained through Arrhenius concept. This is the main limitation of Arrhenius concept. Second is, in addition, it singles out the OH minus ion as the source of base character when other species can play a similar role. So this concept explains us that the compound which contains OH minus ion, that is known as base, but there are other bases are there which doesn't contain OH minus ion, but although they are known as bases only. Therefore, this is the second limitation of your Arrhenius concept. Third one, broader definitions of acids and bases are discussed in the next sections. Here you can see that these limitations are very more large. Therefore, we have to go to second concept, that is your Laurie-Bronsted concept. Now here also Laurie and Bronsted, both of the scientists have as explained what are acids and what are bases. In first one, we are dealing with H plus ion and OH minus ion. Here the concept changes. According to that, the theory also changes. Here, according to Bronsted-Laurie concept, or you can say Laurie-Bronsted concept, an acid is the species donating the proton in a proton transfer reaction. There we are talking about if we can dissolve any of the compound in the water and if it increases concentration of H plus ions. But here we are talking about proton transfer reaction. So here the acid is a substance which donates proton in the proton transfer reaction, and a base is a species accepting the proton in a proton transfer reaction. So according to Laurie-Bronsted concept, acid donates proton while base accepts proton. Then only the whole reaction will be completed. So in any reversible acid-base reaction, both forward and reverse reactions, it involves proton transfer. As we know that in any of the reactions there will be transfer of proton, and therefore we are considered here proton transfer reaction. Now we are taking an example of one reaction. Consider the reaction between NH3 ammonia and H2O. If we react NH3 with H2O, what will we get? That is NH4 plus OH minus. This reaction is a reversible reaction, and both together, NH4 plus and OH minus, both equally get together and reverse back to form NH3 and H2. Again, NH3 and H2 both get together, or you can say react together to form NH4 plus and OH minus. The same cycle will be repeated for the long duration. Here in this reaction you can see that H2O and NH3. H2O has two ions, that is H plus and OH minus. So it donates its proton to NH3. Here from this, H plus is going to NH3. So your H2O, which donates proton, becomes Laurie-Bronsted acid, while NH3, which accepts proton, becomes Laurie-Bronsted base. Now come to this type. Here you form NH4 plus OH minus. When this both react together to form NH3 and H2O, what happened? Here NH4 plus has one extra hydrogen, therefore this becomes NH4 plus OH minus. This has one extra hydrogen, this donates it to OH minus ion. Now you can see that NH4 plus is donating the ion to H plus ion to OH minus. So here NH4 plus is donating, therefore it becomes a Lorry-Bronsted acid, while OH minus is accepting the proton, therefore this becomes Lorry-Bronsted base. You can see that this both acid and bases are interchanging. Here this is the base, this is the acid, while here this becomes acid and this becomes base. Here in the reverse reaction, NH4 plus donates a proton to OH minus and the NH4 plus ion is the acid, while OH minus becomes a Lorry-Bronsted base. Same way here, NH4 plus. What is the conjugate concept? The conjugate acid-base pair concept is explained here. Let us take one example or consider one reaction between NH3 and H2, and what will we get? Let's see here. NH3 plus H2 gives NH4 plus OH minus. Here we know that this H2O donates the ion to NH3, therefore that becomes base. When it comes this side, NH4 plus OH minus. Now NH4 plus has one more hydrogen ion, therefore it donated it to OH minus ion, so it becomes acid. Like here you can see that NH3 is base, Lorry-Bronsted base, but in this side it becomes Lorry-Bronsted acid, right? So same way it can interchange itself, therefore they are known as conjugate acid-base pair, right? Same way, a conjugate acid-base pair consists of two species in acid-base reaction, one acid and one base that differ by the loss or gain of proton. Same way, if you consider H2O, this side behave as acid while this side behave as base. Here you can see that this NH3 is a conjugate base of NH4 plus and NH4 plus is conjugate acid of NH3. Here NH4 plus is the conjugate acid of NH3 and NH3 is the conjugate base of NH4 plus. The Bronsted-Lowry concept defines a species as an acid or base according to its function in the proton transfer reaction. As we know that which donates proton, it becomes acid, and the compound which accepts proton, it becomes Lowry-Bronsted base. Now, some species from this, the next concept which comes is amphoteric substances. What are amphoteric substances, or you can say what are amphoteric species? So when you consider each and every compound can either behave as acid or can either behave as base, but the species that can act, some species can also act as both as an acid or as a base. An amphoteric species is a species that can act either as an acid or either as a base. It can gain also an electron and it can also donate an electron. So it can behave as both, as an acid also and as an base also. For example, HCO3 minus acts as a proton donor in the presence of OH minus. So here it behaves as an acid. We have considered one reaction that is in between HCO3 minus plus OH minus. It gives CO3 minus 2 plus H2O. Here HCO3 minus donates its proton to OH minus ion to form H2O. Here you can see that H3O minus gives its hydrogen ion to OH minus, therefore it becomes H2O and this becomes CO3 minus 2. Now here the same thing will be seen here. When HCO3 is reacting with HF hydrogen fluoride, at that time HCO3 minus plus HF gives H2CO3 plus F minus. Here you can see that HCO3, the HF donates its proton to HCO3 minus, therefore here it behaves as a base because it accepts a proton, while in the above reaction you can see that it loses one hydrogen and therefore it becomes, or you can say it donates its proton, therefore it is known as Lowry-Bronsted acid. Here it behaves as Lowry-Bronsted base. In this way it completes the reaction. So you can see that HCO3 minus can both act as an acid also and can act as a base also. Like it can gain an proton also, and it can lose one proton also. Next example is water. Water is also an amphoteric species. So the amphoteric characteristics of the water is important in the acid-base properties of aqueous solution. As you can see that it is the most widely universal solvent of any of the substance, and it can act as both amphoteric substance. It can act as acid also, it can act as a base also. So here when water is reacted with NH3, H2O plus NH3, it gives you NH4 plus OH minus. Here you can see that H2O has two ions, H plus and OH minus. So it donates its H plus to NH3, so it becomes NH4 plus OH minus. Here water donates its proton, and therefore this becomes Lowry-Bronsted acid, and then it becomes OH minus ion. Now next way, when water reacts with HF plus H2O, it gives you F minus plus H3O plus. Here you can see that your HF will donate its proton to H2O, and water is accepting one proton, therefore this becomes one base. It accepts, therefore becomes base, and in the above reaction it behaves as an acid because it donates its proton, and it forms F minus plus H3O plus. Now the third concept is Lewis concept of acid and base. According to Lewis concept, Lewis the scientist has formed one concept to give the definitions of acid and base. According to that, here in the first one we are taking the concept, or we are taking the example of when any substance is dissolved, or when a compound is dissolved in water. You can say in aqueous solution, we become an aqueous solution. At that time the whole reaction occurs. That concept gives us the concept of acid and base. And second one, we are taking the example of proton transfer reaction, and then we are considered that. Here in the third one, we are considered the electron pair acceptance, or you can say electron transfer reaction. So here, according to Lewis concept of acid and base, according to Lewis concept, an acid is a species which accepts one electron pair, or you can say acid is electron pair acceptor, and base is a species which donates. It donates one electron. So acid has less electrons, therefore it accepts, and base has higher electrons, so that it donates. Therefore this acid is known as electron pair acceptor, while base is known as electron pair donor. Now it creates covalent bond to form one complex. We are taking one example of A plus plus B minus, that is Lewis acid plus Lewis base. Here A plus, that is your positively charged ion plus negatively charged ion. A plus plus B minus gives you AB. The whole complex or the whole compound will be formed here. A plus, what happened here? B has negative charge, therefore it contains higher number of electron pairs, so it donates it to your A plus, which has less number of electron pairs, and it accepts. So this becomes Lewis base, while this becomes Lewis acid. Lewis base is a donor, while Lewis acid is a acceptor. Same way, A plus is Lewis acid, B minus is Lewis base. This is electron acceptor, this is electron donor. And in last, we are getting our compound, that is AB. The bond formed between A and B, both the species, is coordinate covalent bond. Now we are taking an example of the reaction. We are considering the reaction between boron fluoride with ammonia. That is another example of this. BF3 plus NH3 gives BF3NH3, both combines and forms one whole compound. Here you can see that BF3 and NH3, this has one less electron while this has one higher electron, so NH gives it to BF3. So this becomes BN, the whole complex forms, and finally you are getting this one. Here this becomes base because it donates, and this becomes acid as it accepts. Thank you.